is the plane, and it will normally require a common datum and a common datum. And the tolerance feature can never be a center feature, can never be an axis, right? And so here, as we can see from the picture, originally the lead line is at the place as the extension of the dimension line. So this is not correct, right? The lead line should not at the extension of the dimension line. So we need to change the dimension line from the original place to another place. You can change the dimension line. The dimension line originally is here, and we change it to here. So the lead line will not at the extension place. Will not as the extension of the dimension line. And then we write down the tolerance plane. When we make the corrections, normally we do not change the tolerance feature. We do not. So you should not change the circular layout to the causality. Okay, so it's still the circular layout. Because the tolerance feature here is the surface of the cylinder. The circular layout can be measured, can be toleranced. And then, so next is the tolerance value. As we can see, originally it got a phi symbol, diameter symbol, right? So I want you to think about, should this symbol exist? Should this symbol exist? For circular layout, you should first come up with an idea. What's the tolerance zoom look like? What's the tolerance zoom look like? If you are not sure, you should turn to page. Let me see. You should turn to page. Circular. 101. Yeah. One is 104, right? 104. Yeah, 104. For this case, it's 104. As you can see, the tolerance zoom is what? It's the two concentric circles. It's the areas by the two concentric circles. So when the tolerance zoom is like this, should we put a diameter symbol here? As I have stated, only when the tolerance zoom is a circle or a cylinder, we should put a phi before the tolerance value, right? So here, the tolerance zoom is the area between two concentric circles. So no diameter symbol should be put here. So we write down the values here. Tolerance value here. And for circular layout, it requires datum, right? It requires datum. Here, the datum is datum A and the datum B. It's datum A and the datum B. Let's see the datum A. As we can see from the picture, the datum A originally is here. We put a datum here. This is datum A originally, right? And datum B we write down here. So the datum A, datum B, if we see if the datum A is here, datum B is here, what it means? It means that here, for here, the middle line points to this profile line, this contour line. So it means that the data is the surface of the cylinder. The surface of a cylinder can never be a data in real case, so it's wrong. And the data, in fact, should be the axis of the cylinder, right? If we want to say the data A is the axis of this cylinder, where should I place? I should place it here, right? Yeah, I should place the data A here at the as an extension of this dimension line. So this will indicate that the tolerance, the datum is the center feature of this dimension. That also means that is the axis of the cylinder. So this is the correction you should make. And this is also, you should place the datum. Here to the dimension place. Here. So this is datum B. So this means the data A is the axis of this cylinder. Datum B is the axis of this cylinder, and the datum for circular layout here should be the common datum A and B. And so we write down here. This also will also need to change. So this is for the first geometrical tolerance correction. And now let's move on. And here we got the value first, tolerance frame 0.02, and this characteristic. So is there anything wrong with it? So if you are not sure what the characteristic means, you should find it on page 19.2. That's the cylindricity, right?
This arrow is diameter 0.002 or only 0.002?
Pardon?
Actually 0.02.
This value?
Yeah, it's diameter 0.02 or only 0.02.
I have explained only when the tolerance zoom is a circle or cylinder, we should put a phi before the value, right?
Yeah.
But for circular layout, the tolerance zoom is the space between two co-axes, two concentric circles. That means the tolerance zoom is two circles. Is the area between two circles. So the tolerance zoom is not a circle. It's the space between two concentric circles. So you should not put a phi here, and you can find the example on your book. Okay. Okay. So that's
so that's if it's a circle or a cylinder. That is
Yeah. If the tolerance zoom is a circle or a cylinder, you should put a phi before symbol here. And if the tolerance zoom is a sphere in space, then you should put a S phi. It means sphere. Okay. So when you put a phi, you see a phi diameter symbol and phi or S phi. You should think about it if the tolerance zoom fits. Okay. So let's look at the next one. Here, the original label here is the cylindricity. Cylindricity is the one of the form. Is the form. Let me see. Form tolerance. Is one of the form tolerance. For form tolerance, we have said it does not require a datum, right? And clearly, but this one it got some mistake because of what? Why it's not correct? Because the tolerance symbol should always put at the first rectangle, right? Okay. So yeah. So it's a very clear mistake. You just need to correct it. Put the symbol first. Do the symbol first. So for centricity, should we put a 5 before the value? Originally it's 0.02. Should I put for cylindricity? It is measuring cylindricity. So what's the tolerance? You should think about its tolerance zoom. What the tolerance zoom looks like? It's in fact, even though it says this kind of phone tolerance is cylindricity, you should not just think about that the tolerance zoom will also be a cylindricity. In fact, the tolerance zoom is the space between two co-axes cylinder. It's like this. It's the space between two coaxial cylindricity. So the tolerance zoom is not a cylindricity. It's not a cylinder. It's not a cylinder. So we should not add a 5 before it. Okay. And the last one is the circularity. The circularity is also one kind of the phone tolerance. It's also one kind of the phone tolerance. And here, it's all correct, but we just should it also have the same problem as the first one. The lead line should not act as the extension of the dimension line. You just change the lead line place. You change the dimension line. You change the place of the dimension line here. So for this one, it will become correct automatically. Just this is the circularity. For circularity, what's the dimension? What's the tolerance zoom looks like for circularity? Do you still remember? For circularity, it's one of the phone tolerance. Its tolerance zoom will be look like will be two concentric circles. For circularity, the tolerance zoom is the space between two concentric circles. Okay, so no 5 should put here before the tolerance value. So hope you guys understand it. Okay. And we will have 2 more practice during the lesson help you know how to labeling of the geometric tolerance better. Okay. Because it's yeah.
About secure runout and security. What's the main difference? Because all
The tolerance zoom is the same. The tolerance zoom, for name, the tolerance zoom are all concentric circles, the space between two concentric space, but one needs datum and another do not read the data. For circularity, that it does not read the data. That means the center point of the two concentric circles, you can place it anywhere. But for circularity, the center point is fixed. It's determined by the common data A and B. Okay, so generally, for the same, if we measure the circularity error and the circular error for one workpiece, for the same workpiece, if you using the circularity, the circularity error, the error of circularity will smaller than the circular layout. Do you understand why? Because for circularity, the center point is not fixed. It's floating. You can change it, so you can find a smaller concentric circle areas. Okay. You just can float it and try to find the two concentric circles that contain the contour line, and it will be smaller, and the difference of the radius will be smaller. Feature. Tolerance feature clearly here is the circular coin, right? The circular coin. Where is the circular coin? Here is the circular coin, right? This is the circular coin, and it has the geometrical requirement of circularity. So here, if we want to measure the circularity, only here we use a plane to cut the workpiece. We can get a circular, right? Ideally, it's circular, but in fact, it has the circularity error. So for circularity, please remember that the lead line should always be perpendicular to the axis. It should be perpendicular to the axis. In most cases, the lead line is perpendicular to the contour line. It's perpendicular to contour line, but for circularity, it's special. It should be perpendicular to the axis. It should be perpendicular to the axis, and then you continue to labeling it. The symbol is the circle, right? It's a circle. And the next, we write down the tolerance value. It's 0.01. And here, as I have stated, for circularity, we do not need the phi, because the tolerance zoom is the space between two concentric circles. So here we finish the first one, and the next one is the circular coin. Also for the circular coin, the line straightness is 0.02. Here the line is referred to this line or this line. It refers to this line or this line. So this is the tolerance feature. This is the tolerance feature is just these two contour lines. You can choose this one or this one. Here we are labeling here. So for straightness, it's also a kind of form tolerance. It's also one kind of the form tolerance. And for straightness, please remember that the lead line should be perpendicular to the contour line, not like this one. This one is perpendicular to the axis, but for straightness, it's perpendicular to the contour line here. And then labeling the tolerance frame. So torus characteristic symbol is just a line. Straightness for straightness, this is the symbol. And the tolerance value is 0.02. And for this line here, the tolerance zone is the space between two parallel planes. So we do not need to add a phi here. And the next one is the concentricity of the axis of phi D1 cylinder and the phi D2 cylinder, with the common datum straight line of the D1 axis and the D2 axis are 0.005 millimeter respectively. So this is how we labeling the concentricity. If you do not do not know how to label it, you can turn to page 101 for help. And here, first we can labeling the datum, right? Here it has two datum, datum 1 and the datum B. The datum A is the axis of the cylinder, right? So it is a center feature. So it is a center feature. We should put the datum A here and write down datum A. And here we got the datum B. Just remember, you should put the datum. Align with the dimension line. You cannot put it here. You cannot put it here. If you put this place, it means that the datum is the surface of the cylinder, and that is not correct. Okay, this is the datum B. And next, let's see the tolerance, the feature. The tolerance feature is what? Is the axis. Is also the axis. Is the axis of this cylinder and this axis of this cylinder, right? So for the tolerance feature is also the center feature. So we need to put the lead line at the extension of the dimension line here. And try to label here. So we need to write down, here is the symbol. The symbol is two concentric circles, right? This means the concentricity. And here it gives you the tolerance value. And now I want to think about it. Should we put a 5 before this value? There is the 0.05. Should I put 5 before the tolerance value? Yes, right? Because what the tolerance zone looks like. In fact, the tolerance feature is the axis of the cylinder, and the concentricity is limited the axis within a cylinder, right? Within a cylinder, so we should put a 5 before it. And the datum is the common datum A and B. And similarly, for the concentricity of the axis of the phi D2 that cylinder, we should labeling the same. In fact, they are the same. No difference. The symbol concentricity and phi and the common datum. It's a common datum. So we finish the first three, and the next, the plane I has the circularity route with a common data straight line of the phi d axis and the phi d2 axis, and the tolerance value is 0.03. So here we can see that the data is already established, right? But here you should first know where is the tolerance feature. The tolerance feature is plane I. Where is plane I? Plane I is here. It indicates that here. So it means that the tolerance feature is this plane, right? Is this plane. Is this plane. So we can, when we label it, the data is already here. The axis of this cylinder and the axis of phi d2 cylinder. And here, the tolerance feature is this plane. So we should, we can put the lead line to the contour line here. You can also extend the contour line a little bit, so you can label it more convenient. So here, you point the lead line point to the extension line of the contour line and the labeling. Then we put the tolerance frame here. Put the tolerance frame here. And it's the circular route. Please just know that there are two kinds of circular route. First is the circular route, and the second one is the circular route on axial circular route. So here, then we should put the tolerance value here. It's the 0.03, and it has the common datum A and B. Here, because as you can see, on page 105, for circular route in axial direction, the tolerance zoom is the place between two circles in axial directions. So we should not put a phi before the tolerance value. Just remember, just know that for circular route, no matter what kind of type, you do not need to put a phi before it. Okay. So this is the practice one. I will give you 5 minutes to put all these answers on your notebook and see if you still got any question regarding this labeling. Okay, I will give you 5 minutes, and then we move on to next problems, next questions, practice. So is there any question? Which one? You all understand, right? All this name for the name to neighboring the 3 geometrical tolerance. The first is the median plane of the workpiece. The flatness tolerance is 1.015. So first we should know where is the tolerance feature, right? The tolerance feature, it states median plane of the workpiece. So where is the median plane of the workpiece? And Derek and Chen Gong neighboring the flatness of the upper face. In fact, you neighboring the upper face has the flatness tolerance. But here, you all, both of you got a little mistake. You didn't point to the median plane. So median plane is here, right? Because this workpiece is symmetry, and we need to the lead line should point to the, here is the medium plane. So how we indicate this is the medium plane? We should add this dimension line here. This dimension line, then we can indicate the medium plane in this way. The lead line point should serve as the extension of the dimension line. Then we use this dimension to express that this is the medium plane, and then we can write down the tolerance frame. It's for fatness, so this is the symbol, and we put the value here. The value here. Yeah. The tolerance zoom is the space between two parallel planes. And the next, let's see, the maximum deviation of the medium plane of the groove to the medium plane of the workpiece should less than 0.01. So first we got to know what's the tolerance feature. The tolerance feature here is the medium plane of the groove right here. So the tolerance feature should be here. The tolerance feature the lead line should be at the extension of the dimension line. And we can say that it only states the maximum deviation of the medium plane of the groove to the medium plane of the workpiece. Here, we add the data here. This is the data, right? Because it says the medium plane of the workpiece. So this is the data. The data A means that it is the medium plane of the workpiece. It should be used as the data. This is the data and the name. So what is the geometrical characteristic here? It should be the symmetry. If you look at the illustration of symmetry on page 102, you will understand. And here, you just add the symmetry here. The symmetry on here. And here, the tolerance feature, the tolerance value, should I put a 0.01 here or otherwise 1? In fact, we should multiply the given value by 2. And the tolerance data is A. Why I should multiply by 2? In fact, if you look at your book on page 102, you see the illustration of the tolerance zoom. In fact, according to the statement, the data is fixed, and the given value here is the t divided by 2 equals to 0, 1. You can understand? If you understand, you should look into your book, and you will find that according to the statement, the 0.01 in fact equals to half of the tolerance value, okay? And then you should label it like this. And the final one is easy. The upper surface has the parallelism with the lower face, and the value is 0.02. So the upper face is here, the lower face is here. So the lower face serves as the data. You should point, the lead line should point to the counter line. So here we label it the data B, and here we write down the tolerance frame here, and it's the parallel, and then the tolerance value please correct your answers and make sure you understand how the labeling came out. Because the labeling of a geometric tolerance will be a larger part in our tests. So we will have 13 chapter, the chapter 4. And so in last chapter, we learned about the geometric tolerance. And the most important thing you should know is how to label them and know what it means and how to label it. In fact, during the study, you must feel that there are so many geometrical tolerances and they are difficult to measure. In fact, you can think about how we measure the geometrical tolerance. In fact, in these days, we use a machine to measure it. For example, for the circularity, we got a circularity meter to measure it. There are specialized machines to measure certain geometrical tolerances. And some are old-fashioned, manually measurement, and some can measure by specialized machines. And we will doing 2 experiments later and measuring the perpendicularity and parallelism. And here I will show a video that we always use this kind of machine to measure the geometrical tolerance. It's for general purposes. Let's see. It's called the 3D measuring machine. It's called the 3D measuring machine. I will use the. It's a device advertisement of a 3D measuring machine for the Windsor. It's a little bit like a 3 machine center, but this machine is specialized for measurement. As you can see, it got all kinds of probes. It can select different probes and it starts to make the measurement. As we can see here, is the workpiece we want to measure. It got a very complicated geometrical features, and here he just used the probe to touch it. When it touches it, he record the data. It's a 3D XYZ data in the computer, and he will measure many points to generate a profile of the workpiece. So, you see it touch the surface, the plane, touch the plane of the piece. So you can think about how the machine uses this data to calculate the specific geometric tolerances. For example, for a plane here, he may take different points here, and to see to calculate the fatness, right? And here there are the holes. He may take different points. Around the circle, and he can calculate the circularity. And as you can see, it will switch different probes. Some probes are small, and it can be used to measure smaller places, small holes. As as you can see, it's measuring the circularity of the shaft. It can be seen as a shaft. Here, the different points can be used to calculate the circularity. So, normally for important workpieces, after it has been machined, it all need to go through the inspection. And the inspection of the geometrical tolerance is all automatically. And after the measurement, the important geometrical tolerance is the value will be calculated, and we will know if the workpiece is acceptable. Okay, here's the end. So now, today we are going to learn the final chapter of our lesson. That is the surface roughness. And I'd like to tell you is that next week we are going to do 2 experiments, and the week after next week we are doing another 2 experiments. And at our last lesson, last class, we are doing the test. Okay, so this is our last theory lesson. And if you want to know if you're ready to pass the exam, you can check the exercise we have done. If you know how all the tests, all the exercises we have doing during our class, you will sure pass the exam. And so let's move on. In this chapter, we are on the 5 parts. First is the basic terms and the definition and the evaluation parameter of the surface roughness. And the third is the graphic symbol for the indication of surface texture. The fourth is the composition of a complete graphical symbol for surface texture. And the final is the inspection of the roughness of the surface roughness. So first, I'd like to think about the influence of surface roughness on a workpiece. Normally, different things will have different surface roughness. For example, a notebook, when we touch the surface of it, you will feel that different notebooks have different surface roughness. It represents the quality of the notebook, right? Because the MacBook always have the top quality, and because it's machined by very high precision machine, and other brands may have a little bit lower quality. But in fact, this kind of thing is only affect the appearance, does not affect the functioning. Because our laptop computer does not require it to transfer the force or make. It's just for appearance. But in fact, in mechanical industry, the surface roughness have a very important effects in many aspects. First, the surface roughness will affect the friction. Friction. You can think about if this is the horizontal axis, is the roughness. This represents the friction. So you can think about if the roughness of the surface increased when two parts move relatively, the friction will increase or decrease. Increase or decrease. With the increase of roughness, the friction will increase or decrease. Decrease. Think about if the
roughness. If roughness is increasing,
yeah
then it will increase.
the roughness. Think about just it become very rough. There are
Like this.
ups and downs,
Ups and downs.
and the two workpieces are move relatively. The friction will increase or decrease.
Friction between two.
Yeah.
Obviously,
Increase. Yeah. Normally, in most cases, it will increases. But have you? I think it's easy to understand, right? Because the it's more rough. The surface is more rough. Then it's the friction is will be more friction, and it's in most cases it's like this. But have you had this kind of experience when you use a knife to cut an apple, cut a fruit? The half of the apple may stick to the knife. That's when the apple is first cut. The roughness is very small, and the roughness is small, but the friction is big. It can even hold the apple onto the knife, right? So when the roughness decreases to certain value, it will increase. It will increase. So in fact, the real situation is like this. With the increase of roughness, the friction first drop and then it increase. So the friction is very the friction will affect the wear of a workpiece a lot. Why? Because if the friction is big, then it more easily become wear, right? So the surface roughness will affect the resistance to feel of the workpiece. And second, we have all learned the feed type in chapter 3, right? Chapter 3 or chapter 2? Chapter 3. In fact, it's chapter 2. We have learned the feet, right, in chapter 2. And we know there are different types of feet. For example, the clearance feet, the transition feet, and the interference feet. So, if it is interference feet, so if the feed type for two workpieces, the feed type is the interference feed. It means that they need to connect tightly, right? But if it has the let me set another example. If the feed type is the clearance feed, it means that they will rotate. They will have a relative motion normally, and if the surface roughness is increasing, is becoming bigger. So what will happen? In fact, for clearance feet, if the roughness value is big, then they are more easily to become wear. They will easily to get wear. When the wear happen, the clearance will become larger, right? So when we consider the feet of workpieces, the roughness will affect the stability of a feet, because at first the feet is the tolerance zone is okay, will meet the requirement, but because the roughness, if the roughness the value is big, then it will more easily to wear, and the clearance will increase, so it will affect the stability of feet. And it will also affect the fatigue strength, because if there are many peak and valley, then it will more easily to be affected by the oxidating force, and it will more easily to fatigue. And also, if there are many big peak and valley, the water and oil are more easily contained in this place, and it will be more easily to get corrosion, and it will affect its feeling property. And the roughness will also affect the appearance, its optical performance, electrical and thermal conductivity of the workpieces. So the surface roughness is important, and it will affect so many properties of the workpiece. So now let's learn the terms and definition of surface roughness. First, when we try to get the surface roughness, we first got the surface texture. The original is surface texture. Then we use a plane to cut the surface. Then we can get the surface profile. This is the surface profile. The surface profile, in fact, it consists of three parts. The first is the form error. This form error we have learned in our last chapter, geometrical tolerance. This is we got the form tolerance. So when the pitch value is very big, then the corresponding component is called the form error. Then we have the waviness and the roughness. How the three components are defined? Then here, the roughness is for the pitch smaller than 1 millimeter. For waviness, the pitch is from 1 to 10 millimeter, and for form error, the pitch is greater than 10 millimeter. So for the original geometrical texture, we'll use a plane to cut it to get the profile, and the profile includes three parts. For those pitch larger than 10, it's the form error. For those pitch between 1 to 10, it's the waviness. And for those pitch smaller than 1 millimeter, it's the roughness. So how we measure the roughness. And we need to sample the profile. There is the definition of the sampling length, LR. It's the length in the direction of axis used for identifying the irregularity characterizing the profile. Normally, the length of LR contains 5 peaks and 5 valleys of the profile of the profile. And the evaluation Ln is usually equal to 5 times of the LR, 5 times of the sampling length. The related roughness parameters are calculated using this profile, or this now profile. Next is the center line of the profile. The center line of the profile is the baseline for identifying the surface profile. So this length is the LR, and we need to, how we get the center line? We normally use the least square feet. That means the data on the profile, the distance, we calculated their distance to the line and try to minimize it. So the corresponding line is the center line. Then is some parameters we can calculate it using the profile. There are profile peak. Profile peak is the outwardly direction. As see, this is peak, this is peak, this is peak. This profile, those profile above the 0 is the peak. Then we also got the profile valley, is the inward direction. As you can see, this is valley, this is profile valley, this is profile valley. And in this profile, we can get the height of the assessed profile, and it's called the ordinate value z. And for this profile, we can get the profile peak height zp is the distance from axis to highest point. So in this profile, the highest point is here. It's maybe not that correct, but here is we treat this point is the highest point. So the distance between this point to x-axis we call the profile peak height zp, and this is the peak z, and p means the peak. And we also have the profile valley depth. That's called zv, because v represents the valley. It's the distance from axis to the lowest point. Here is the zv. Because this point is the lowest point. We also have the profile. These parameters, like zx, zp, zv, are all measuring the profile in z direction. And we also got a parameter to measure the profile in x direction. That is the profile element weight, xs. Xs is the length of an axis segmented intersection with the profile element. So here is the xs. In fact, we have many xs can be estimated for this profile. For example, here we got a peak here, got a valley here. So this distance is the xs. This distance is xs. This is also xs. This xs. In fact, for this profile, we can calculate a number of xs. But for zp and zv, there are only one, because it's the highest and lowest point to the x-axis. So now let's learn the evaluation parameter. First is there are two kinds of parameters. There are amplitude parameters, and there are also spacing parameters. For amplitude parameters, we got the RA and RZ. These two parameters for evaluation of roughness is the most commonly used and the most important ones. The RA is the arithmetic mean deviation of the assessed profile. And here is the calculation equations. So how it is calculated? We can see it calculates the profile. There are many points here, and their distance to the x-axis, and integrally and divided by L. So it's the arithmetic mean deviation of the assessed profile. And RZ is the maximum height of profile. That's the RZ. RZ, in fact, is equals to ZP plus ZV. Is equals to, because this is the highest point to axis. This is the lowest point to x-axis. And you add them, you get RZ. You get RZ. And for spacing parameters, we use the RSM. RSM is the mean wise of the x-axis. Is the mean wise of x-axis, because I have said here we got many x-axis values. We average them, and then we get the RSM. Now I want to think about when is this parameters big is better or smaller is better in most cases. So these two parameters is used to measuring the amplitude of the profile, right? And the spacing parameter ISM is used to measure this distance, the average of this distance. There are many, this one. So when the amplitude parameter is smaller, we will treat the profile will have the surface is more smooth, right? And it's not rough. When the value is small, right? And when the value is big, we can think that it's very rough. So for these two values, clearly the smaller the better. So how about this? In fact, for this one, is also the smaller the better. Because you want the peaks and value, they are more tight. And then, in fact, it will have a better performance. Next, we will learn the graphic symbols for the indication of a surface. Here is the basic symbol, and here is the basic symbol. Normally, we do not use this symbol alone, and in most cases, we are using these three symbols. This is indicated by the surface you can get the surface of the workpiece by any processor node. And here you will write down the related requirement. And this is for material removal requirement. We add a line here. So what is material removal? In fact, the turning, milling, drilling, this kind of machine process are all material removal, because the tool cut the workpieces, and the material of the workpiece is decreasing, right, during the process. So for this kind of process, when we get the surface, the related requirement, we need to put a line here. And here is the no material removal. We put a circle here. So do you know any process is no material removal? So, do you know about the casting? Yeah, when the metal is melting and it put in certain I don't know mold and this process no material is removable, right? So for this workpieces is no material removal. Then let's see the composition of a complete graph symbol for surface texture. This is a complete graphic symbol, and here A, B, C, D, E can all labeling related requirements. Here A we are labeling single surface texture requirement, and B here we labeling 2 or more surface texture requirement. C is the manufacturing method. Sometimes measuring the turning, milling, casting, different manufacturing method. And the D is the surface layer and orientation. Here some examples. If the surface the orientation is in this direction, we put this symbol here. This is perpendicularly, then we add this sign and the x direction and the circle direction, and this is a multiple direction to the M. And E is the machining allowance. Here are some examples of the labeling of roughness. In fact, the labeling of roughness is very likely the labeling of the direction of the labeling is like the labeling of dimension. Normally we just horizontally labeling, and then we can also labeling vertically. So when you labeling vertically, it means it can be labeled like this. So for this labeling, do you know what it means here? Here, all these examples have all upper limits. It all have an upper limit for the roughness. So if it only labeled one requirement here, it means it has an upper requirement. It means that the roughness of these planes should not exceed the labeling values here. And here the value is not the millimeter. The unit here is micrometer. This is the micrometer.
Yeah.
This is the micrometer, right?
Yeah.
Yeah. So the value here is not is the micrometer, not a millimeter. If it is a millimeter, it's a very it's very big. It's too big. Okay. So, and I will take 2 examples here. This is the RA. So this means this surface, the roughness of this surface should not exceed RA 1.6. RA, as we stated, is the most commonly used parameters for roughness. RZ is also very commonly used, but this is more common. And the RZ, that means this face and this face. The RZ, we use RZ to measure the roughness of these 2 faces, and it should not exist 12.5 this value. And as we can see, it has different values here. So there are tables. We can select the specific values on. You can find it on page. Let me see. It's on page 100 and 13.8 and 39. On these pages, one table is for RA, and another table is for RZ. These values are derived from the preferred value series, and you can, when you need to neighboring you need to find the close value, you need to choose this value from these two tables. It cannot be select as you wish. You can just select specific values from these two tables. And let's see another example. And here it has the RA. It is used to have set the roughness requirement for this plane. And here the RZ, it has the roughness requirement for the surface of the cylinder. For the surface of the cylinder here. And another example, as you can see, it has, I think it has some, this one is not good. And when we labeling the surface, and we do not need to labeling all the surface, labeling all the roughness requirement for the surface. For majority of the surface having the same text feature requirements, you can labeling like this. For these workpieces, as we can see here, Z are this surface requirement for the surface of the hole, and this is the roughness requirement for the shaft. And also, in fact, we may have a requirement for this plane, this hole, this shaft. It can all have the roughness requirement. We can write it, right? If the rest surface have the same surface requirement, we can label it like this. This is it means that we use the material removal method to get the surface, and the tolerance value is 25, and then you use RZ to measure it. And put a bracket here, and using this symbol. And it means rest of the surface have the same roughness requirement, and the requirement is using this to express. And here is a detailed drawing of a gear. As we can see, many places, these different planes and different here, different shaft plates have different roughness requirements, and the rest of the planes that are not indicated specifically, then we can use this symbol. It means that the rest of the planes or shaft or holes have the same roughness requirements. Just write down like this. And use the bracket and put this symbol near to the title bracket. And next, I will show you some ways how we measure the roughness. First is the stylus. You can get the roughness using the stylus instrument. For stylus instrument, it has the stylus. It's just like a probe. It can probe around on the surface of the workpiece, and you can use the electronic devices to magnify the displacement of the probe, and it can generate the profile on the computer. And it can also called the roughness meter. It's a very high precision measurement, and we are doing the experiment next week. Next week we are doing experiment how to measure the roughness. And after it get the profile of the workpiece, the computer can calculate the related parameters RA, RZ, RSM automatically. Because all the data information is gained, and then those parameters can be derived. For those workers in a workshop, they may do not have this kind of machine, and this machine normally located in the QA offices. But for field worker, they need a faster inspection. Normally, they will use the standard samples. They just compare the surface of the workpiece with the standard samples to compare it using the touch feel or an eye inspection to see if the surface is can pass the requirement. The next one is we can also use the optical instruments to measure it. It does not require a probe, just use graphic measurements to measure the surface of the test workpiece, and it will normally generate a picture, and it can also get the parameters for roughness automatically. And here I will show you a video of how the roughness can be measured using the optical instruments. It's also an advertisement of a roughness meter.
Hi, I'm John. I'm a Zygo applications engineer. Today, we're here to demonstrate the Z-Gauge optical profiler in the most challenging of circumstances.
Optical
On a
profiler.
rickety plastic table in a machine shop full of noise and vibration. Traditionally, roughness measurement tools are locked away in a QA lab. The Z-Gauge is a scanning white light interferometer designed to work on the production floor. Our test sample is a sealing valve from the automotive industry. It's got a very fine machine surface. We'll be measuring roughness in 3 dimensions, not just 2, unlike a stylus profiler. Other tools may compromise vertical resolution based on the magnification that you choose. The Z-Gauge maintains high resolution at all magnifications. So we'll place the part on the stage. The software has a very nice autofocus feature. What it's doing is it's scanning through the surface looking for optimal focus. Once we have that, we're ready to take a measurement. And when I do this measurement, I'm going to be pounding on the stage, inducing vibration. This would normally cause other measurement tools to fail.
It works like a microscope.
In just a few short seconds, we'll have a 3D surface map of the data. And here in the 3D plot, I can locate the data. The surface roughness
This is the profile we
are
learned.
ISO 25178 compliant. In addition, we have the 2D profile slice that we can drag around into the cross section at various segments throughout the data.
You can inspect different places, inspect the profile line in different
So,
places.
that's the Z-Gauge in a production environment. Give you 3D surface.
And you can see there are some values changing here. In fact, it's not clear IRZ, and these values are all calculated according to the ISO standard.
These values are ISO 42870 compliant. So, that's the Z-Gauge in a production environment. Give you 3D surface roughness measurement with nanometer level precision. Or about the cost of a cabinet stylus profile. Not affected by the environment. You can take your measurements out of the QA lab and put them right next to your production equipment. It's easy to use, anyone can do it, and you don't need a specialist. Also, there's no expensive satellite to use up or break, saving your costs and downtime. Increase your precision, decrease your cost, and save time. It's kind of ideal. If you'd like to see a live demo of the Z-Gauge or any of other Zygo
just now, what we show is an optical instrument, and normally the precision of optical instrument is less than the stylus instruments. But in this video, it claims it can be nanometer, and that's right. That's even better than normal stylus instruments. And let's have a break, and this is the final lesson for our class. And later on, I will talk a little bit about our exam and the experiments.